So today we're going to be starting I really like this unit. We're going to start out with exponentials, and we're going to be dealing with exponentials and logarithms. You did exponentials in secondary math 1, reviewed them in 2, and then we're reviewing them again in 3. So an exponential function, you guys, will have the form y is equal to a times b raised to the x. Oh, it's on 3. No wonder. Okay, saying that again. 8-1. So exponential functions have the form y is equal to a times b raised to the x. So a couple things to note. A is not raised to the x. Only b is raised to the x. You may see it written with parentheses like this, a times b raised to the x, or you might not. Either way, same thing. So a is what we call our initial value. B is our growth or decay factor. It's going to be exponential growth if our b value is larger than 1. So we're going to be getting exponentially larger and larger if that b value is larger than 1. And we're going to be getting exponentially smaller and smaller. It's called exponential decay. Your b is smaller than 1. So you have to be careful though, because we can't assume just if it's a fraction that it's decay. For example, 3/2 is a fraction, but that's 1.5. So that would be larger than 1, that would be growth. So we've just got to be really careful when saying if it's growth or decay. All right, so everybody flip to page number 5. It says, is this exponential growth or decay? So, and then also it asks what the y-intercept. So I just want to say one more thing. Looking up here, if we plug something in, we plug it in for x, and we get something out, correct, for y. Making sure we understand that. Okay, so here we go. Looking at number 5. We would say this is exponential decay because the only thing that matters is the 1/2. Our b value is the only thing that matters. Nothing, a does not matter whatsoever. So because 1/2 is less than 1, it's decay. So this would be the work we'd show. So everybody, think about why that makes sense. If we plug in a 1 right here, that's 2 times 1/2 raised to the 1 power. Isn't 1/2 to the 1 power just a half? So aren't we taking 2 and then dividing it by 2 essentially? So it's getting exponentially smaller. Okay, so this is decay. And then our y-intercept is always when x equals 0. So our y-intercept, showing our work, is when x equals 0. So let's plug that in and do some algebra. I'm going to scroll up for those of you in the back. So we would have y is equal to 2 times 1/2 to the 0 power. What's any base to the 0 power? 1. I like that you said 1, not 0. So this is 2 times 1. So y equals 2. So our y-intercept, we plugged in 0, got out 2. So we could write it as a point. 0, xy, so 0, 2. That's our y-intercept. Now notice, that is our initial value, isn't it? Any base to the 0 power is 1. We plugged in 0. Because of y, right, yeah, anytime I say to you, no matter what the function is, even if I gave you a random function, if I said to you, what's the y-intercept, you just plug in 0 for x. It's when x equals 0. Okay, looking at number 6, is this exponential growth or decay? Remember, 3 does not affect the answer whatsoever for growth or decay. This is growth, and you'd say it's growth because 2 is larger than 1. So this is getting exponentially larger, which makes sense. Let's plug in a 1 just for fun to think about it. 3 times 2 to the first. Isn't 2 to the first 2? 3 times 2 is 6. So do you see how if we start at 3, we would then go up to 6? So it's getting larger exponentially. Okay, so it's growth. Our y-intercept is when x equals 0. So what's my answer going to be? 3. So we plugged in 0, got out 3. Guys, is everybody able to see it? 2 to the 0 power is 1. So do you see how it's just 3? Our y-intercept is going to be our initial value for non-shifted exponentials. See, number 7, exponential growth or decay. We only look at 1/6. 1/6 is less than 1, so this is exponential decay. Our y-intercept is when x is equal to 0. So we're going to get 0, what? 1/4. Plug in 0. 1/6 to the 0 power is 1, so that would go away. And we get 1/4. So this one is also decay because a half is less than 1, so it's exponential decay. And our y-intercept is our initial value, which is 3. So we would say 0, we plug in 0. and we get out 3, x, y. Okay, what I want you to do is 22. That's your homework problem. So just do it in class. Do 22, ready, go. Well, we're not done learning. Like, we're bouncing back and forth. Like, we're doing. Exponentials are one of the most real-world used problems in the real world. In fact, I taught this completely differently until my students were really struggling with it in a previous year. And then I sat down with my mom, who hates math, loathes it, she's not good at it. And I was like, this makes no sense for my students. I wonder how I can help make it make more sense. And she said, think of it like this. Like, that makes total sense. I'm like, whoa, that is so much easier. So my mom taught me how to teach it to people and make it easier. Okay, so we know that exponentials have this form. Y is equal to a times b raised to the x, where this is our initial value or our starting point. B is our growth or decay factor, and if b is larger than 1, it's growth, and if b is less than 1, it's decay. So I want you to think of your b, your factor, your growth factor, as a percent of growth or decay. So for example, if we're gaining 20% interest versus losing 20% interest, we're going to look at our growth and decay factor here. And I'm going to make sense of it. So everybody listening very carefully so that this makes sense. If we started with $500 in the real world, and I said to you, you're going to get an interest rate of 20%. Okay, everybody listening? This is not on your worksheet, you're just looking up here. So if I say we have $500 and you're going to gain 20% interest in a year, aren't we getting 100% of that $500 back? Meaning we're getting fully $500 plus more, correct? Plus 20% more. Does everybody understand? So that would be, as a decimal, we write percents as decimals to actually calculate. So that would be 1.2. That would be 120%. Does everybody see? So then if I plugged in 1 year, you could calculate how much you're going to get after 1 year. Let's all type that in. 500, do it. 500 times 1.2 raised to the first power. So how much money after 1 year? $600. Perfect. Let's plug in 2 years, just for fun. So you would type 500 times 1.2 raised to the second power. How much money are we going to have in 2 years? 620? Oh, 720. So do you see how this is working, guys? Okay, so this 1.2 meant 120%. 100% plus 20 more. So really it just meant 20% more. Does everybody understand? Okay, so look right here. This is where people mess up. If I said to you, given $500, you're going to lose 20% interest. You would not do this. 500 times 0.20. You would not do that. Aren't we we're only losing 20% interest. So aren't we taking its full value, its 100% value, and subtracting 20%? So that's 80% of its worth. Does everybody understand? So you're doing 500 times 0.80. So let's plug in after 1 year, how much did that $500 go down to? $400. Let's plug in 2 years. 320. Awesome. Do you see how that's working, everybody? So this is a decay factor of 0.80, but it was decaying by 20%. Does everybody understand? Okay, awesome. So here we go. Number 9. Let's just start applying it in the real world. This is very, very applicable in the real world. So it's kind of nice because it makes total sense. I used to get all technical with it, and if you just think of it like that, like my mom said, it makes total sense. So it says on number 9, you put $2,000 into a college savings account for 4 years. The account pays 6% interest annually. Write the equation. So we would have our exponentials have this form, a times b raised to the x, where a is your initial value. So we would write y is equal to, how much initial money are we putting in? 2,000. So you would go like this, 2,000. And then our growth factor is a 6% interest. So 100% plus 6 more percent, correct? Now careful, so that's 106%. So as a decimal, that would be 1.06. Does everybody understand? Not 1.6, that would be 160. That would be 60%. And then raised to the 4. Okay, good. So when we type that into our calculator, and I do want you all to quickly type it in, you should get, after 4 years for your college savings account, you're going to have $2,524.95. So we went from 2,000 to adding $524.95, and that's just sitting in an account. Fun story for you. This is a true fact, okay? So wouldn't you rather have your money sitting in here than under your mattress? Making no interest. So this is a true story. My grandparents, so my great-grandparents, they didn't believe in banks and they were very wealthy. They made a lot of money. They owned their own company. So they didn't believe in banks, so they would get all their money they would put in their house, and they had nowhere to put it, so they would stuff it in like mattresses. They would put it in walls. They would do all these things. So after they passed away, my grandma and my mother and all that, they sold their house. They thought they had got all the money out of their house. Well, a few years later, my mom also teaches high school, but not math. The student came to her that their family bought the house, and the student said, "Did you know that when we were renovating, we found money in the walls?" And my mom was like, "Really? How much?" And they said, "We're not going to tell you." And they wouldn't tell my family, but they said it's a lot of money. We found a lot of money in the wall. So because they had bought the house, it was their money. And they never told us how much, but they found that money. So if you just think about, though, the reason I tell you that story is, how dumb, because all that money was sitting there. Let's say they had $2,000 sitting under the mattress or in the wall. They could have had this much money about 4 years later if they would have had it in the bank getting interest. You get what I'm saying? But anyways, true fact for you. Interesting, huh? I know, it's their money and they wouldn't tell us, and they said it was a lot of money. And then there they were going on vacations and Ritz with a yacht. Just kidding, I made that part up. Okay. All right, here we go. Do problem number 10, ready, go. I don't have any. Okay, do you guys have this as your answer? Was this your equation? Yep, and then this one you got? Okay, let's move on. Okay, oh no. This is number 10. You're supposed to do number 10. Is that what you got for number 10? Okay, somewhere wrong. But do you have that equation? So maybe you just typed it in wrong. Okay, so number 11. Here we go. This is really different. So everybody watch. I mean, it's the same but different. So it says, you invest the $2,000 in a college savings account that pays an interest rate of 4%, same as before. You make no future deposits or withdrawals, because if you did, then you're going to be dealing with some different things here. But A, it says, how much will you have in 3 years? Okay, so we've got to figure, okay, so how much will we have in 3 years? This one's the same, actually. So here we go. We would write out our work, though. 2,000 times 1.04 raised to the third power. So we'll type that into our calculator. How much will you have in 18 years? So 2,000 times 1.04 to the 18. So if we type that into our calculator, this one, we should get this. $2,249.76. So on an ACT, if they said how much money did you gain, you would say $249.76, or about $250, right? Okay, if you calculate that in your calculator, you should get $4,051.65. Perfect. It's in 18 years. I mean, it's better than nothing. It's better than having it hidden under your mattress. Okay, number 12. This is where it's different. So everybody watch. It says, suppose you invest $2,000 in a savings account that pays at a rate of 4%. So we have y is equal to, our starting money was 2,000, 1.04 raised to the x, right? Okay. So now on A, it says, how many years will it take for the account to contain 2,500? So now, isn't this the ending amount? So that's got to go here, correct? So you're going to say 2,500 equals 2,000, and then 1.04 to the x. Now, here's the thing. Algebraically, since this x is an exponent, there's no way to undo that. You can't divide by the base. That's not algebraically how these work. So we don't know how to solve these yet, and we're not going to know until we know how to do logarithms. So let's solve by graphing. Can't we always solve by graphing, especially if decimals are acceptable? So let's solve by graphing. So what you're going to do, because math is very literal, you guys. This is saying, when does this function equal this function? So go to y equals, and in y1, we're going to type that in y2, type that in, and then we're going to see where they intersect, where they're equal. So we're using our graphing calculator. So everybody watch, pull up your graphing calculator. Here we go. Go to y equals. In y1, type in 2,500. In y2, type in your other function. And we want to know when they're equal. Now think about it, guys. This is a straight line at 2,500. So our window, our Y max, meaning how high up we can see on the Y axis, needs to be well above that. So everybody go to window, go to Y max, and let's change it well above 2,000, was it 2,500? So I typed in 3,000. Now notice they don't have to be equal. Like I don't have to make this, I wouldn't make this negative 3,000. You know what I mean, everybody? And then I just made sure that I have some room for X min and X max, like some decent room, negative 20 and 20. Now I hit graph. So look, here's my line, here's my exponential function. We want to know when they're equal, where they intersect. So you'll do second trace, go down to intersect, second trace, go down to intersect, and then it says first curve. It's on the line, so we'll hit enter. We don't have to do anything. It says curve. It's on the exponential, so we're good. It'll do it for us. We don't have to do anything. Hit enter. Then it says, do you want me to guess? Hit enter. If it ends up in the right spot, the intersection is at 5.7, right? 5.7 years. That's how much time it took, 5.7. 5.7 years. What did you mess up on? Oh, you put plus. Okay, got it. Okay, now understand, this is an acceptable answer. So that's 5.7 years. But on an ACT, this is what I see most of the time. And really, we should be able to think a little bit advancedly. Isn't this mean 5 years and 70% of a year? 0.7 means 70%, right? So let's get technical and let's get down to months. So 5 years and then 0.7 of a year. So how many months are in a year? 12. So we want 70% of 12. So type, in your calculator, type 12 times 0.7. What is it? 8.4. So that means 8 months. Does that make sense? 5 years, 8 months. And then we could even get down to days, because we have 0.4, but we're not going to do that. But understand, let me show you what an ACT I've seen as an answer. I've seen 5.7, I've seen them say 5 years, 7 months, and that's what most people choose, because they see 5.7. But we would have got it wrong on the ACT. They do it to trick you, because it's not 5 months, 7, it's not 5 years, 7 months. It's 5 years, 8 months. Does that make sense, everybody? You get what I'm saying? Okay. So now it says, how many years will it take for the account to contain 3,000? So instead of 2,500, we're putting 3,000. So now I want you to go to your calculator, go to Y1, change that to 3,000, and do the second trace again. Yeah. Yeah, well, we can't. That's why solving by calculator is only acceptable if we can do decimals. Does that make sense? So we did say 5.7 years, but then we converted it ourselves. Does that make sense? Yes. Let me push pause here.
Like 10.2.
Guys, what was this? 10 years? So you got 10 points, what years? 10.2 years. So we would say 10 years, and that means 20% of a year. So how many months? 2. No, we can't say 2 unnecessarily. So take 12 times 0.20, right? Which is 2.4. So this one was 10 years, 2 months. It just happened to be that way. Does everybody understand what we did there? Were you all able to get that? 10.2. Okay. So we could get down to minute, we could get down to days, we could get down to seconds. Yes. Sure. Okay, so number 13, it says the population of this grows at 1.2% per year for 15 years. Watch, this one tricks people. So it's a growth of 1.2%. So let me show you what people mess up on. This is 100% plus 1.2%, right? So that's 101.2, right? Percent. So to change that to the correct decimal, we would move it back 1, 2 places, right? That's how we change percents to decimals. You guys knew that, right? So that's our growth factor, 1.012. That is how we have to write that correctly. So our initial population is 120,000. Our growth factor is 1.012, and then raised to the 15. So So when you type that into your calculator, we should get this. 143,512.24. Okay, yeah, absolutely. So what I was getting at is people mess up on the growth factor. But do you see how I just did some algebra real quick to get it correctly, everybody? Because right here, this decimal is the right one for only 1.2%. Yeah, right. And that what I see people do is this. The reason I went over this is because I see people do this as the growth factor. They'll do 1.12. Do you see how that would be 12%, not 1.2%? So that's why I went over this one, is because that would be the wrong growth factor. It's got to be that to make it 1.2%. Okay, awesome. Looking at this one, a population of this decreases 1.5%. So it's the word decreases. So remember to do 100% minus 1.5%. Yes. Yep. We're just making sure we can get our growth and decay factors correctly because it's kind of hard sometimes. Okay, so 100% minus 1.5%. Isn't that 98.5%? So to write that as a decimal, you'll move your decimal 2 places, right? So 0.985 is our decay factor. Isn't that less than 1? So we would start out with 1,860,123 times 0.985 raised to the 12th power. And when you type that into your calculator, I don't know, I didn't do that one yet. So just read me out the number if you've got it. Like 1, 2, 3, 4, 5. Like 1, 5. Perfect. So then I do that, go in 3, go in 3. You know what I mean? Just to make it easy on myself. Okay. So guys, look and see if your answer makes sense. We started with this, and it went down to this after 12 years. So it sounds about right. It didn't go down by very much, right? If we're only going down by 1.5%. Okay, awesome. Okay, so it says, this is the last one, and I'm going to let you just go for it. Here we go. A classmate, so everybody watch, because this is what tricks people. So it says a classmate says that the growth factor of the exponential function y is equal to 15 times 0.3 to the x is 0.3. What is their mistake? So first of all, it's not growth. That's the first thing, right? Decay isn't 0.3 less than 1. Yeah. So the first thing is to say 0.3 is less than 1, so this is decay. But that's still not necessarily, we've got to think about, that is our decay factor, but how much is it decaying by?
30.
No, it's worth 30%, right?
Yeah, it's worth 30.
This is 30% worth of 15, right? So didn't it go down by 70%, everybody? Yes. So you would say, this is our decay factor. You guys, not to get confused, but it went down by, or it decreased by 70%. Do you get what I'm saying, everybody? Okay. Because if it's only worth 30%, it went down by a full 70%. Okay. So you're going to do 23 through 24, go for it. So it says, write out the growth or decay factors. Now these are all plus signs, so that means they're all growth. So remember that we write percents as, it wants to see if you can write it as a decimal correctly. You know what I mean? So adding 45%, that means it's growth of 45%. So our growth factor would be 1.45, wouldn't it? That's that easy. So that's all you got to do with that one. Those ones. Okay, everybody look at 26 with me, because this one takes a little bit more thought. So it says, in 2009, there were 1,570 bears, and really try to take it in instead of just writing down the answer because I'm doing it. I'm trying to help you understand, like when you see something different, how to do it. So in 2009, so I'm just going to write out some things. In 2009, we have 1,570 bears. In a refugee. In 2010, we have increased to 1,884 bears. 1,570 went up by that. So isn't it a growth factor since it's going up? Okay. It says if the trend continues and the trend is increasing exponentially, how many bears in 2018? So what we're looking for is how many bears. So let's set up our equation here. Exponential times the form. Y is equal to a times b raised to the x, where a is the initial value. So aren't we starting here?
Yeah.
So 1570 is our starting point. We have no idea what the percent is right now, correct?
Yes.
So let's just put b. And then we have, in the end, after from 2009 to 2010, in the end, don't we have this?
Yeah.
So that would be our output, correct? 1884. I like what you're saying. That's 1 year difference, isn't it? So we know this is 1. So now solve for b. So get b alone. We'll divide both sides by 1570. Divide by 1570. And then we have 1.2, isn't it? Equals b to the first power. So b to the first power is just 1, right? So b equals 1.2. So aren't we increasing by 20%? So we just use algebra to solve. So we found the factor. So now we can go back and figure out in 2018. So let's start over. Our new equation will be y is equal to, our initial value is this, 1570. Our factor is 1.2. Raised to the, don't just say 18. 9 to 18 was 9 years. So this is 9 years later. So now we type that in, and the number of bears we're going to have approximately is, so we just, you get how we set this equation up? Yeah, so we have b to the first, so we just solved for b using algebra. So we divided that by that. So we got 1.2, because that divided by that is 1.2, and then we have b to the first. So then b to the first is just b. So you have how many bears? 8,100 bears. Yikes, I don't want to be there. That's a lot of bears. That's increasing by 20% each year. Right? So if I said to you, how much is it increasing per year, you'd say 20%, right? Not 120, you'd say 20%. Okay, so now you're doing 27 through 32. And that's where I'm gonna stop, because I don't want to rush you. So I want you to get as much done on 27 through 32 in class as possible. The rest of that is homework up to 32. You get what I'm saying? No? Anything we did in class is what's due. Anything not, so you're basically doing the whole back page. That's the homework. So I want you to get as much done. Yep, that's it. The whole back page is homework. And then we're going to finish up next time. But I just don't want you to be rushed. I want you to understand before we move on. So the next 10 minutes, get as much of those done as possible. Ready, go.